the Mobius function via the sum of factors. So if we were to restrict k to the primes, to just the primes, we can replicate Mobius, the Mobius function, doing this.
Hello, and thank you for watching my video. This is called Quadratic Polynomial Number Theorem, and it is a generalization of Euler's pentagonal number theorem, and we'll see what that means for known results, and we'll look at some new things too. And this is a submission to 3 Blue, 1 Brown's Summer of Math Exposition 1, SOME1. Thanks, Grant. This guy and gang for inviting me.
Okay. It is fundamental to the theory of partitions that if we were to take this Q series and restrict the index in some fashion, we're going to leave some of the k's out, that we're going to get on the other side here something where we have a restricted partition function. It can't count more than partitions than there are. It can only count less when we take k away. To see an example of this, let's presume our k's we're limited to, say, 3, 7, and 11. We would have 1, and this is the denominator, which would give us, just spotted an error there, this should be plus. Right. Let's go ahead and take the inversion of that. A sequence where we got all positive, and so if this is a subset of this, then what are these? Well, let's look at the numbers. 0, 1, 2, 3.
3 is a partition of 3, 3, 3 is a partition of 6, 7 is a partition of 7, 3, 3, 3 is a partition of 9, and 3, 7 is a partition of 10. So we're just counting partitions into parts made up of 3s, 7s, and eventually 11s. But let's take another example, a little bit smaller, but we'll take a look at the inverse, aka the indicator sequence, and see if we can make sense of it. How does that information, what's behind the information in the indicator sequence? Let's take a look.
Just consider that k equals 2, 3, and 7. Then this denominator would be given by, and that's our final answer. A finite sequence of length 7 plus 3 is 10 plus 2 is 12 plus 1 for the empty set gives us a length of 13. So if we start with 0, we should end up with 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Capital LR equals 13. Get where we get an indication, which is 2, 3, 4, 5, 7, 9, 10, 12. And notice the correspondence. Well, we got 2, 3, and 7, and we've got negative 1s for those. And here we have this 5 with a positive 1. And here 9 and 10 with positive 1s. And here 12 with a negative 1. So what's going on? Well, long story short, essentially it's because 5 equals 2 plus 3. And odd number, and this is just like the Mobius function. We're getting a negative 1 because these are primes and a single factor of this. But again, because we're adding, we're not, when we get to this point, we're talking about adding. So 5 is given by 2 plus 3. 9 is given by 2 plus 7. 10 is given by 3 plus 7. And so for each of these we have two numbers that add. So with the 2, negative 1 to the 2 gives us a positive 1. Here it's just one number adding to these, so it's negative 1 to the 1, which gives us a negative 1. So if 12 is negative 1, then that must be 3 factors, right? Because we've gone from positive to negative again, 2 factors. That must be 3 factors, and of course, yes, 2 plus 3 plus 7 gives us 12. So that's what our indicators are indicating, are these combinations, the possibilities of these 3 factors adding up, and if a number cannot be composed from them, then it's going to be a 0. So our restricted set of partitions that come from restricting k to these values should be given by the inverse of this. Let's do that. Let's invert this finite sequence that we have as we did before. We get the sequence
1, 0, 1, 1, 1, 1, 2, 2, 2, 3, 3, 3.
3, 4. So slowly growing sequence, and by this we're saying we restricted the k to these 3 finite factors and gives us a finite indicating sequence, which we saw is the combinations of adding these 3 factors, and that if we invert it, then we get this positive sequence. What we said about restricting the index resulting in restricted partitions, this sequence is a subsequence of that. Let's examine this example. So we have our empty set. Insert our sequence above here for reference. 2, 2, etc. K equals 2. And here's one that's just 2, and it's counting 1. Look at 1. We don't have a 1, so 1 is 0. And in these partitions we have a 3, and then we have a 2 and a 1 and a 1, 1, 1. Well, 1 doesn't count. 1's not included. 1 is a 0 in our indicator sequence. So there's only one partition corresponding to the 3 for the k equals 3, and so on. So here we've got 1. Well, 4 is not in the works, and we know that anything with a 1 is not in the works, leaving us this one here with just 2's. So we can go, well, 1 doesn't count, so anything with a 1, forget about it. And we might suspect that, well, because we have 5 is composed from 2 plus 3, and we have an indicator, that this one should count. But that is not the case. It's strictly partitions into parts made up of these numbers. Partitions that are made up solely of these. So our 5 doesn't count, and neither will any of the other combinations. It's strictly partitions into parts made up of 2s, 3s, and 7s. So if we go for 6, we can quickly identify that these are the 2 parts that that number is referring to. We go to 7, we've got 7 itself.
And then we've got, what do we have? Well, nothing with the 1s. 4 and a 3, neither do.
Look at that. I have used this to identify a mistake, and that is, I forgot one here. 3, 2, 2, and that's, oh, there's 2. And so you can follow this out, and you're going to get the same logic. So by restricting to k equals 2, 3, and 7, we are restricting to partitions that are made up of 2s, 3s, and 7s, period. And those numbers of the number of partitions, the restricted partitions, are going to be given by this sequence here. Pretty cool. The Mobius function, by the way, is going to equal 1, 0, or negative 1. It's going to be 0 if n is not square free. So if it's divisible by 2 squared, or 5 to the 4th, or 7 to the 3rd, so a square free number has no repeated prime factors. So if it has any repeated prime factors, it's going to be 0, and if it has an even number of prime factors, then it's going to be equal to 1. And if it has an odd number of prime factors, it's going to be equal to negative 1. And even though this is defined formally as on products, we can see that we're getting the same thing in terms of the addition of factors, or the addition of numbers. Only in this case, even if we included a squareful number in here, let's say 12, which is 3 times 4, 4 being square, the Mobius function would count it as 0 in terms of the product, 3 times a square. But in terms of what we're doing here, it's just another number as far as addition is concerned. If we were to add 12 to this mix, we'd get a longer thing here, and we would have probably, I'm guessing we'd get 0 here, because we would have 12. We would have the 12 representation, and we would have the 2 plus 3 plus 7 representation. Thus we would get a, no, actually we'd get a negative 2, wouldn't we? Because we'd have a negative 2 for this and a negative 2 for that. But the point being is that once we get to partitions, then we're going to be counting partitions into parts that are equal to either 2 or 3 or 7 or 12. And the whole square free thing doesn't impact that. But the interesting thing is that we have an isomorphic, or we have a connection, we have a correlation to the Mobius function via the sum of factors. So if we were to restrict k to the primes, to just the primes, we can replicate Mobius, the Mobius function, doing this. Okay, so check this out. In our scheme, we can actually use and create an algebra where we say that this is, as we did before, that this is the number 1, and that this is the number 2, and that this is the number 3, etc., etc. And so if we wanted to do a primorial, where we're just going to factor together 3 primes, then we're going to have 2 times 3 times 11, etc. And the sequence that we get is going to look like this. So this is this product here is in essence is our primorial, like a factorial, only we're restricting to primes for all primes less than or equal to r. And so what this and what that ends up looking like is going to be 2 times 3 and we can do a symmetry check. We have 1, 2, 3, 4, 5 factors, so we are flipping signs in our symmetry, and so we should be 1, -1, 0, and then boom, and then yes, 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 and then yes. So our symmetry is intact, which is a nice way to check for errors without too much trouble. And so this is valid, and as we saw before, well, that's 11, so 12, 13, we can say that these are the accurate numbers in our sequence. Once we get to 13, that's going to end up being a 0. But look at what's happening here. Let's go with let's just look at our index 0, 1, 12, and we can just do this. We can say, well, 2 can be composed by 2. There's only 1, so we get a -1. We can't compose anything with primes to get 1, so that's a 0. And then for 3, we just have 3, and that's all there is. We can't, 2 plus 2 doesn't do it, and there's nothing else available. So there's only 1, and so that's -1. 4, we can't, 2 plus 2, we're not going to do that. Product realm square-free numbers, when we convert and transform to this sum realm, we can't have multiple adders. We can't have 2 plus 2. They have to be distinct. So that's the important codicil and the connection to the Mobius function, the sum form of the Mobius function, essentially. So nothing for 4, and for 5. Wait a minute. It's 0. Why is it 0? Because if we have 5, then we have a -1, right? Well, no, because we have a 2 plus 3, which is a positive 1, because there are 2 summons. So -1 plus 1 gives us the 0. For 6, we have 3 plus 3 doesn't work. And we have 2, 3, and 5 to work with. 5, we can't do it, so it's 0. Nothing happens here. 7 is itself a prime, so that's a -1. So because this is 0, that means that we must have something with 2 summons that we can do, and obviously that's 2 plus 5. So this comes down to the number of ways that a specific number can be written as the sum of primes, which is very, very cool. For 8, we have a 1, which corresponds to just 3 plus 5. There are no other ways, so we only have 1, but it has 2 summons, so it's a positive 1. For 9, we have 2 plus 7, and there are no other ways to have distinct primes sum to 9, so that's a positive 1 because there's 2 summons. For 10, notice that we can do 7 plus 3, so we get a positive 1. So we must have a negative 1 somewhere, right? And we do, because 7 itself, going back, look, 2 plus 5, and so we have 2 plus 5 plus 3, and so we get a plus 1 for this, and now we have an odd number of summings, so we get a negative 1 for that, so we sum to 0. For 11, there is only the one possibility. 2, 7, can't do it except for 11 itself, so we get a negative 1. And for 12, right off the bat, we can see that 5 plus 7, 5 plus 7 gives us 12, so, and that's 0, so we have to have more than that. And then just look at our 5, 2 plus 3, so we have 2 plus 3 plus 7. But even that, 7, well, can we do 2 plus 5? We can't, because then we'd have 2 2's, etc., etc. And so, as it turns out then, there are only 2 possibilities for 12, one of them with 2 summons to give us a positive 1, one with 3 summons to give us a negative 1, summing to 0. In essence, we are accounting for all of the square-free numbers. We're just adding the factors here rather than multiplying the factors here.
Okay, this is a lot of blah blah blah. I was basically going off on a tangent, and it did end up causing me to discover something that I'm excited about. I'm going to add that as a special bonus episode after this.
A different sequence, obviously, but let's look at mu k. 1, 2. 2 is square free, 3 is square free and prime, 4 is not square free, 5 is negative 1, 6 is 2 times 3. It's a square, it's square free, but it has 2 factors, so that's going to be a 1. 7 is a negative 1, 8 is squareful, 9 is squareful, 10 is 2 times 5, so this is a positive 1, 11 is a negative 1, etc. And then if you then sum those, negative 1, negative 2, 0, negative 1 plus negative 1, negative 2 plus 0, negative 2, negative 3, negative 2, negative 3, negative 3, negative 3, negative 2, negative 3, etc. So following this sequence out, the contention is that by the time we get to R, we essentially, that this number that appears here, the running total, is less than radical R. That these cannot accumulate to get a running sum that's any bigger than this. Because of the symmetry relationship, whenever k, or the number of factors, is odd anyway, we know for a fact that our accurate elements are going to be matched with a sign change over here on the tail end, right? So this plus this is 0, leaving just the thing in the middle. Now this middle section does grow very large compared to these, but these grow pretty darn large themselves. And so in here, in the mix, is this balance of reframing the sum over this index straight up, sum over that index, and accounting for the contributions in different ways, where we're counting some here that are in the future, that are greater than R. So we can take this and we can look at how we might reorder this to to establish this. There's lots of neat things that we can do in this, basically because of this symmetry relationship. These always equal 0 when you sum them together, and so do the middle numbers, because every interim product, every partial product, always sums to 0, regardless of whether it's odd or even. It just works out magically that way. It's not actually magic, but no time to stray any further. Just wanted to point out is that this is what I would call mathematical hotness. Applying what we know, we can take the inverse of this and get the number of partitions of n into prime parts. So let's do that. If we substitute a bold or some kind of symbol of a number to mean that it is equal to this, then we can define these numbers to be something we call, something I call, this is quintegers. They're just individual factors of Q series, of all Q series, in integers, positive integers, are made up of these. And in that regard, because the placeholders are unique over the natural numbers, they are like primes. All of them are like primes. 1 over quinteger R primorial is itself a Q series. It's just a representation of that product, where K is restricted to being among the prime numbers, and that's what we get. So we should have 1 for the empty set, dot, and etc. So we get that. We get 1, 0,
1, 1, 1, 2, 2,
3, and etc. So this becomes a very general principle by which we can construct restricted partition functions of just about anything we please. It just comes down to a matter whether it's useful, interesting, gives you some new insights and things like that. I am grateful to the Summer of Math Exposition project and the idea of it, that here's a place where we can informally share mathematical teachings and information and research in a less formal environment, without a bunch of poppycocking and hogwashing. And so I appreciate the opportunity to show what I've got going on, and that's it. Thank you very much for watching my video.